So I'm going to first of all derive the arc length formula because we are in calculus and that's pretty cool. So in an algebra class, you would say you would get 2 points and you could say, I want to find the distance between these 2 points. You could find the distance of this line using the Pythagorean theorem, saying that this is your y value and this is your x value. And so if you said this is y, this is x, you could say this s or this r, call it r. Uh, we could say that r is just y squared y squared plus x squared square root, right? Because this is just our distance formula. This is our Pythagorean theorem. And so, what if we didn't have a straight line, but we still wanted to find the distance of a line? Well, we are learning in integral calculus that we can basically break things up into small units. And if they're small enough, if we make them small and smaller and smaller, then eventually we're going to get the total number of whatever. So if we said, let's take this segment of line here and just call this dr for a small section of this function. And so dr has a width of dx. This has a width of dx. And you can see why. There's a tiny change in x over this arc length here. And it also has a tiny change in y, which I'll label in blue, I guess, dy. As a tiny change in x and a tiny change in y. There is indeed a slope. So we know that if we can just add up these tiny little lines, we can get the total arc length. The arc length is just the sum of these tiny little s's, or these tiny little drs. So arc length, arc length is equal to the integral of I'll just keep it dr. Well, we want everything in terms of y's and x's because that's what we know how to do. We don't know how to integrate this because we're in the x and y world. So let's go and figure that out. We know that from here that r is just the square root of x squared and y squared. So let's rewrite this equation in terms of that. So instead of x's and y's, it's dx's and dy's because we're doing tiny, 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 tiny changes. So we're going to do the integral of square root of dx squared dx squared plus dy squared. And this is a bit weird to look at, but we can do some algebra here. And this may be unintuitive to some of you. So but when you look at it, you can kind of understand where I'm coming from and why I do this. So what we can do is we can factor out a dx. We can factor out a dx squared from this. So if I pulled out a dx from this first term, maybe write the radical here. if I pulled out a dx from this first term, a dx squared actually, we're gonna basically be dividing this by dx squared. So that's just 1. And here is just dy divided by dx. So that's dy dx, which is y prime. So I'm going to write y prime squared. Y prime. Actually, to keep the notation consistent, I will do dy dx. dy dx. And then the dy dx is squared. And now we can do some cool radical things. We could say this, we could just pull it outside the radical. Say, hey, the square root of dx squared, that's just dx. So we could pop this outside the radical here. And we can now integrate. We can now integrate this function once we do that, because we now have a dx on the outside, so we can integrate this in terms of x. So we have the integral of a radical of 1 plus y prime squared. Y prime, we'll do like that, y prime squared. And then we're going to do this in terms of dx. We are doing this in the x world. And this is the formula for arc length. We can now just substitute whatever numbers we need. If f of x was squared, let's go do that. Let's say f of x is x squared. It kind of already looks like a parabola. So y is equal to x squared. So what we need y prime. We need y prime. Take the derivative of x squared, that's just 2x. So now we could say the integral of the square root of 1 plus y prime, which is 2x, but we need to say the quantity, 2x, the quantity squared. And then we can integrate this with respect to dx. And this will probably be something that you would want to type into a calculator. But this is how you would do an arc length question.